Again, a perfect place to stop there. We've set up this example problem. I've set up my iteration process. I've just learned over the years, go ahead and draw yourself a roadmap, because you will get through this process and you will lose yourself and you'll wonder, what in the heck are we trying to do again? Go back to this. This will help you. I promise you. Draw this out on your paper. If you're taking an exam with me, if you'll draw this out, you show me, hey, this is the process I'm going to use to get there. I guess what I would suggest to you is at this point, if this were a test problem, and normally I do put an iteration problem on an exam, either guess the diameter, a lot of times it's find an unknown diameter. Basically, you're at about 60% of the points on that problem. There's not too much, and that's not too time consuming to get to that point. Go look up these unknown properties. Right? Go look up, we're going to need to know the viscosity and the density of this water at 40 degrees Fahrenheit. Go look that up. That's the next thing we're going to do. We're going to need to know epsilon for a rubber hose. You do all that and you're going to get really close to 80% of points on this problem before you actually do the grunt work of trying to find the answer. So don't let this intimidate you. And again, when I'm grading this, I don't put a ton of points in actually doing this. I put a ton of points showing me you know how to do this. So don't let that frighten you. But you have no chance of doing this if you don't practice this on your own. Find a problem. Try to solve it without any online resources. Just yourself, your calculator, and your book. See if you can set one of these up. Okay? But here's a nice example we can use to work our way through this. All right, let's keep going here. Okay, so as I said, we need to go now get some of these properties. I need viscosity and density for water at 40 degrees Fahrenheit. I need to get epsilon. I need to start plugging some unknowns in here. I've kind of set up, I've done the engineering work, so to speak. I solved the problem. Now I just actually need to put a solution to it, an actual numerical value. To do that, I need some properties. So you should have property tables somewhere in a text, right? I've seen this before. I know you can't really see those too well there, so I'm just going to pull these off. I've got properties. Since I have water at 40 degrees Fahrenheit, again, for a liquid, I just need to know the temperature. I'm going to use saturated liquid water at 40 degrees Fahrenheit. Density is going to be about 62.42 pound mass per cubic foot. And the viscosity is going to be, water's got a really low viscosity typically. This is 1.038 times 10 to the minus 3. Sorry, I didn't write that very well there. The units on viscosity on mu is going to be pound mass per foot and also per second. So that's 1.038 times 10 to the minus 3. Right? And the other thing we're going to need here is we're going to need epsilon for a rubber hose. So I have a rubber hose. I'm going to go find my epsilon value. And our text is suggesting the epsilon in English units for a rubber hose to be about 0.00, let's see, it's 4033 feet. Could we have worked this problem in metric units? Sure, could. Works the same in English units. So, and all these measurements came out in English to begin with, so it's a heck of a lot less work to try to convert it over. Had we measured everything in metric to begin with, fine, but we didn't, so here we are. Okay. So far, so good, right? Let's see, what do we do from here? Well, here's what we can do. Right? We can guess. Our first guess, and normally I can make a terrible first guess. And I need my tablet back because I've got a Moody diagram on there that we're going to need. Okay. So you can normally make a terrible first guess, and this thing will converge pretty quickly. Okay. Now, here's the thing about a first guess. You can start anywhere on this process with a first guess. You don't have to guess a volumetric flow rate and do all your calculations. You could actually guess your F value or your Reynolds number to begin with, if you like. That's kind of what I'm going to do. Is I'm going to start, I'm not going to guess an actual flow rate. I'm just going to guess roughly what I think the Reynolds number should be. I can tell you, looking at this siphon, the outlet is going to be reasonably turbulent. So if we assume some level of turbulent flow at the outlet, let's see if that gives us a reasonable guess at F value that we can work through. Okay, so let's do that, shall we? So if I guess, well, let's find epsilon over d. Let's start there, right? So this is 0.000033 feet divided by, right? No, that's 1, 2, and 8 zeros. It's 4 zeros. Here, let's just write it correctly. 4 zeros, 33 feet divided by 3/4 of an inch divided by 12 feet. Convert this to feet if you like. I normally just keep it around because it's not a rational value to begin with. So, okay, calculator. Here we go. Let's do 3/4 is 0.75 divided by 12. And I'm going to invert that. So this whole bottom converts to 16. That makes sense. 16 times 0.000033. Okay. So I'm getting epsilon over d to be about it's 3 zeros, 528. That's my relative reference. All right. And let's see if I don't actually, on this Moody diagram, I don't have a line for that. But we can get pretty close, though. It's going to be between a couple of lines here. So I've got, again, that is 3 zeros, 528. So it's between, I've got here a line for 3 zeros and a 4 and 3 zeros and a 6. It's going to be somewhere between those two lines. Let me see if I got a stylus that works any better. My finger. So somewhere in here, if I say that flow is completely turbulent, right? Let's say it's a high Reynolds number out here somewhere. I really don't know. Again, it's just a first guess. So let's say, we know our epsilon over d is going to be somewhere kind of in this range here. Right, so let's say that's my first guess, is it's just turbulent flow. So somewhere in here we're just going to come over and say, well, that's where we're going to start as my first guess at F. Looks like about 0.017. Okay, so I'm going to use that as my first guess at F. Let's just start a new page. Oh, running out of room here. Okay, page 3. These problems get long, guys. This is normal. It's just how it goes. So, problem, let's say page number 4. Okay. Again, our first guess. We're just going to guess F to be about 0.017. What flow rate achieves that? I don't know. And I don't really care. It's just a first guess. It doesn't have to be good. So I'm starting here at this point in the loop the first time through. I'm going to use that with my energy equation to get a flow rate. Okay, now this is where we're going to have some algebra involved, and that's okay. Okay, so I'm going to go back to this expression over here. Okay, I can plug in v squared here now if you like. Man, it's going to be a lot of algebra. That's okay. I'm trying to figure out, as I'm writing this, I'm trying to figure out the best way to do this. Okay, all right, well, let's say that this is going to be, I'm just going to plug this in. Let's say Z1 is equal to 16 v dot squared over pi squared d to the 4th. Right? Plugging this in here. Multiplied by 1 over 2g plus FL over d 1 over 2g plus some KL 1 over 2G. As I'm setting this up here, I just realized I don't know this one. Man. Okay. Somewhere, right, I'm just going to write here, forgot to find some KL. Right. Forgot to find some KL. Okay, let's find some KL. So if we look at this thing, I've got a pipe inlet basically, and I've got a bend here. 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 plus one more. I've got 9 bends, 9 180-degree bends. And I've got 1 pipe inlet. Now, I don't think we're going to have anything. All right, so what are the KL for each of these? All right, we're going to have a KL total. I don't think we're going to have exactly these in our chart here. Let's see what we got. All right, well, we've got 180-degree return bends there. Okay, 180-degree return bends. These are not threaded fittings. They're not really flanged fittings, but you can see the difference in the values there. The threaded fittings are going to have a much larger loss. The flange fittings tend to be reasonably smooth. I think that's going to be a pretty reasonable estimate. Let's say that a 0.2 is pretty reasonable. There's a bunch of bends there, and every one of these bends is going to lose some energy. 0.2 might be a little bit much, but I think it's a reasonable assumption. I'm going to have 9 of those. This is 1.8 for all of the bends. Now, the pipe inlet, even less clear based on what we have here, but I mean, there's this guy. We don't exactly match these parameters. The pipe's pretty far into the pool, but this isn't a real huge KL value. It might be significantly smaller than this. Let's just kind of plan this speed. I think this KL would be kind of the worst case scenario for us of this pipe inlet for us. So let's just say 0.8 is a reasonable estimate. We're making assumptions here, but we just do want to just make sure it's clear that there is going to be some minor losses here. So what is that? 2.6. Some KL, the total there, we'll say approximately 2.6. That's a reasonable estimate, I think. Okay. So if I go back up here then, let's continue. Again, we're going to say if we guess F to be about 0.017. Now let's manipulate this guy a little bit here, and let's see if we can, let's just pull that V dot out there, can we? Man, okay, algebra. I think we'll get there. I'm going to go ahead and pull this 2G out, because it's 1 over 2G. I'm going to put it in here with these guys, so let's move everything over. Yikes. Okay. Let's just do this. Let's say V dot squared. Must be a little easier to visualize, I think. I'm going to move the 2G, because it's on the denominator all the way across here. I'm going to move it over to the numerator the other side. So the 2G is going to come over. 2G times Z1. Also in the denominator in each term is a pi squared and a D to the 4th in every one of those terms there. All right, I'm going to have to pause it there. We'll pick up here in a second. Come in.